picked up the kids last night, got out of the car, my glasses were.
Yeah, mine too, yeah.
Yes.
And I didn't have a mask on.
Yeah, exactly.
Really good.
We are ready to go, so whenever you guys are ready.
Okay. Well, thank you everyone for being online or physically present for David Loveless, Ph.D. defense. David came here in 2014 from my alma mater, the State University of College at Oneonta, for a program in meteorology. He got his master's degree using ground-based observations to look at boars, working closely with Tim Schmidt. Since that time, there's been a great partnership between Tim and David, so I'm going to let Tim say a few words as well before we begin.
Tim Wagner.
Tim Wagner, yeah.
That's right, yeah. No, it wasn't Schmidt that did the Bohr project, it was also me.
Well, yes, right.
Yeah, but, so everyone in the room knows who I am, and for those of you online, I'm Tim Wagner. I'm a research scientist at SIMS, and I've been working with David for a number of years on projects involving ground-based remote sensing. This is a particularly cool project that we're doing right now because it's combining ground-based with satellite. But David and I have had a number of adventures over the years. The first time that we met, you want to show the picture, we didn't actually meet. This was the AMS annual meeting photo that appeared on the AMS webpage for a while. You can't quite see it because it's sort of washed out here in the picture, but there's David and there's me. We didn't know each other at the time. We just happened to sit next to each other at the big plenary session at AMS. But we actually met, do you remember where we actually met it for real?
Was it in Pecan?
Yeah, it was in Hays, Kansas. It was the first time we actually spoke during the Pecan Field Project. Since then, David has done great things, come to Madison, got his master's, worked on this wonderful PhD project, met his wife, had some twins. He's certainly had a big full life up to this point, and so it's exciting that we've reached this level that we're now ready for the next big stage. And I'll just go ahead and let you tell everyone everything you know about synergizing ground-based and satellite observations.
Great, thank you, Tim. Thank you, Steve, also for the introduction. So yeah, I'll be talking about developing a synergy of ground-based and space-based infrared sensors in order to improve thermodynamic sounding of the planetary boundary layer. So the motivation for this talk really comes from National Research Council report in 2009, and also kind of more recently the Decadal Survey in 2017 that notes that satellite-based sounding of the planetary boundary layer is largely inadequate in both accuracy and resolution for the purposes of numerical weather prediction, nowcasting, and general monitoring of severe weather. So to give you a sense of what these retrieval errors are like from satellite-based sounders, this is a validation study of the new CAPS retrieval, which is NOAA's operational retrieval for polar orbiting IR and microwave sounders. And so you can see that temperature here on the left, new CAPS is generally within 2 Kelvin of radio sound observations throughout most of the atmosphere until you get to the surface, where there's these really large errors of 2.5, 3 Kelvin, sometimes even greater than that. And then on the water vapor mixing ratio side, they're reporting their errors in percent. So these, the 15 to 20% errors in water vapor near the surface kind of translates to something like 2 to 3 grams per kilogram in environments that are kind of typical for the continental U.S. So returning to these reports, basically both the National Research Council and Decadal Survey say that it's important to address these problems. And the National Research Council actually outlined a solution to this problem, saying that we should develop a nationwide network of ground-based thermodynamic profilers in order to supplement the existing space-based observing system. So I'll throw in Dave Turner's ARIO-E retrieval here to kind of give a comparison. So the ARI is a ground-based sensor that we'll be talking about later on in this talk. And basically you can see that Dave's retrieval is within about 1.5 Kelvin in the bottom 2 kilometers of the atmosphere and within 1 grams per kilogram in the bottom 2 kilometers as well. And You can imagine that that would be a nice supplement to what's currently offered by NUCAPs throughout the rest of the atmosphere. So to give a specific case study here to kind of understand the problem a bit better, this is a comparison of temperature and water vapor, temperature on the left, and water vapor on the right. A radio sound observation is plotted in black. In blue is the NUCAPs retrieval, and the red is the ARIO-E retrieval. And what we see is that on the temperature side, NUCAPs is not even able to identify the existence of this nocturnal inversion, whereas the ARI is able to recreate that inversion relatively nicely. On the water vapor side, you see that NUCAPs is quite an accurate depiction of the water vapor profile above 800 millibars, but below that has quite significant errors, and supplementing the area near the surface would dramatically increase your accuracy of that water vapor profile. So for a quick background on IR sounding, these instruments will essentially make measurements in radiant space, and then you use some prior knowledge of the distribution of trace gases in the atmosphere that have absorption lines within this spectrum. So things like carbon dioxide and ozone and water vapor. And from that, you could start making estimates about the state of the atmosphere. So for example, the ARI radiances are plotted in red. Again, that's the ground-based sensor. And carbon dioxide is very highly absorptive. And so essentially, ARI becomes very sensitive to the near surface layer, and this layer is relatively warm, and therefore ARI measures relatively high radiances. Contrast that with CRIS, the space-based sensor, so top looking down, you end up with sensitivity in the stratosphere and upper troposphere, which is relatively cold, and therefore measures much smaller radiances compared to what ARI measures in the same spectrum. So you can see that the measurements from these two sensors largely mirror each other throughout the infrared. And ultimately, what we're getting at here is these are very similar instruments with different perspectives, and so combining them should provide more information about the atmosphere than either instrument operating alone. So there's two studies that I kind of want to highlight that have looked at combining space-based and ground-based sensors into a combined retrieval. That is one retrieval from which you're putting in multiple measurements from multiple instruments into it. And so the first one here is from Kirsten Ebel in 2013. Basically, she combined a ground-based microwave radiometer with an assortment of IR and microwave sounders on the ground and in space. And the thing that I want to highlight in these figures, basically she's plotting the synergy benefit, so the gain from adding, say, ARI or AMPSI or Severi, Yazi, etc., with the ground-based microwave radiometer. The big thing is, despite the ground-based microwave radiometer having much greater signal near the surface than, say, a space-based sensor like Yazi still offers improvements in total information content compared to the ground-based radiometer operating alone. And those improvements are even seen near the surface. So the synergy of two sensors together is much better than, say, using ARI below some level and CRIS above another level type of thing. So the second study I want to point out is Toporov and Lohner that kind of applied this synergy between a ground-based radiometer and space-based IR sensor. And they kind of used reanalysis data and developed a synergistic retrieval and kind of assessed how these different sensors different sets, combinations of sensors were able to identify trends in CAPE. So the black line here is essentially the truth, and so you can see that there's this region, this period of time where there's much greater CAPE than relative to the rest of the time frame. And what I want to point out to you is this green line, the combination of the ground-based radiometer with the space-based IR sounder, is able to have a really good depiction of this increase in CAPE, whereas the space-based sensor operating alone does not identify that increase in CAPE at all. So what I want to focus on in this study is extending information content analyses in clear sky conditions to multiple climate regimes. So Kirsten Ebel's study focused on a single site in Germany and only looked at 100 profiles. We want to get much greater number of profiles and across numerous climate regimes. In addition, we want to look at vertical resolution of the synergy and kind of quantify those gains, since the decadal survey sets goals for vertical resolution of retrievals. Next, we'll look at cloudy sky scenes a little bit, and then lastly, we'll end with a case study where I develop the combined retrieval and try and look at it using real observations. So we'll start with our clear sky study here. And as I mentioned, we want to look at multiple climate regimes. So we utilize radio sound profiles from multiple atmospheric radiation measurement program sites located throughout the world. And then we're going to quantify the benefits of the synergy in terms of degrees of freedom, which is a measure of information content, vertical resolution, and uncertainties. So we get our profiles from a continental site in southern Great Plains, in Oklahoma, a maritime subtropical site with the East-North Atlantic located in the Azores Islands, and then also in the North Slope of Alaska, offering us a polar environment. And we'll utilize a 6-year period of these radio sound observations. You can see the various locations of them here. And ultimately what we do is basically any profile that has a single point of relative humidity being greater than 90%, we flag it as possibly containing a cloud. And so we end up with 3,765 clear sky profiles at SGP and a little over 400 profiles at the other two sites. Basically, this difference is because SGP launches 6 and 18Z radio sondes, whereas the other two stations don't, so you ultimately have double the radio sondes in the data set there. So instrumentation that we'll look at. We're going to focus on the infrared because it has greater vertical resolution because you have more absorption lines there than microwave sensors. And so we'll use the ARRI, which has a long legacy of development here at SSEC as our ground-based sensor. And we're going to look at combining that with the ABI imager on GOES 16 and 17, mostly because it's the only sensor in geostationary orbit that over North America that currently provides any bit of sounding information. We have our standard AIRS, CRIS, and IASI, so the typical polar orbiting IR sounders. We'll include all three of them, and then given the interest in moving toward IR sounding from geostationary orbits, we include the GEARS sensor, which has been recently put into geostationary orbit over Eastern Asia on the Fengyun 4 satellite. However, it has the noise that it has is a bit greater than what we'd expect from UMETSAT or NOAA's future geostationary IR sounders. So we'll utilize this GIFS instrument, which was a proposed sounder to be in geostationary orbit. So we'll basically apply the GIFS noise characteristics to the GEARS instrument to kind of make that noise more in line with what we'd expect from UMETSAT and NOAA in the future. So a quick comment here on why we're including all three polar orbiting sounders. They're very similar, but they have differing spectral resolutions and different noise characteristics. So ultimately, we want to include all three because including all three in a realistic applied retrieval would maximize our matchups with ground-based sensors. And ultimately, we want to see if those varying characteristics spectrally in terms of noise translate to any changes in information content in the end. So for radiative transfer modeling for this part, we want to use a fast model because this makes it practical to run our analysis over such a large number of profiles. So we'll utilize this model called OSS, which is essentially a lookup table derived from LBL-RTM. We'll use constant trace gas profiles of carbon dioxide, nitrous oxide, ozone, and methane for all the profiles that we simulate, ultimately to make sure that the variations are only caused by variations in say vertical resolution and information content, are only caused by variations in the thermodynamic profile that we're inputting. And then water vapor is a very important absorbing gas in the IR, and that's allowed to vary with the inputted radio sign profiles. So then we'll use the CAML, the NASA CAML emissivity product to input surface emissivity for our radiative transfer modeling. And then we use the AIRS 101 pressure levels, ultimately because it's quite a popular pressure grid to use in space-based sounding communities. And however, we did find that this degrades the information content that the AIRI provides because it has such coarse resolution near the surface. And I'll touch on this a bit later. So quantifying degrees of freedom. Degrees of freedom is our measure of information content, so it measures the number of independent pieces of information provided by the signal of an instrument. And so to calculate that, you need the averaging kernel, where K is the Jacobian, so the change in radiance, so let's say a change in temperature at each level or change in water vapor at each level. And then we'll use the instrument noise for our error covariance matrix. Then we have this a priori covariance matrix, which we calculate from the clear sky profiles from each site. So ultimately, this SA variable is the same regardless what station we're calculating averaging kernel score. And so in the end, the degrees of freedom is equal to the trace of the averaging kernel. So this is the sum of the diagonal elements to tell us the number of degrees of freedom. So there's a couple shortcomings to this methodology that I'd like to highlight. Notably, using instrument noise only for our error covariance matrix results in an overestimation of information content. However, we do this because modeling errors are very difficult to quantify, and that's, we kind of need to make some assumptions here to make it simpler to do. We also aren't accounting for spatial variations in temperature and water vapor that space-based sensors in their larger field of views are going to be sensitive to. And then lastly, we're inputting the skin temperature and surface emissivity into the radiative transfer modeling. However, the ideal retrieval would retrieve those quantities at the same time as retrieving temperature and water vapor. So you could imagine, say, inputting skin temperature into the retrieval would also increase uncertainties and decrease information content for temperature and water vapor that I'm going to show you here. So we're going to look at some box plots here of degrees of freedom across the full troposphere, which I'm describing as the surface to 200 hectopascal layer. So what you see, so in black is the individual instruments operating alone, and then in red is the area combined with each instrument, each space-based instrument respectively. So what we see is that ARRI and the polar orbiting IR sounders and really GIFs as well provide quite similar information content across the various scenes that we have here. In fact, I want to point out that AIRS, Chris, and Yazzie, despite their differing characteristics, have almost identical information content. At least that's what I'm finding. And then when you include the ARRI in the, I should point out ABI has relatively little information, ultimately because it is an imager and not a sounder, so its broadband channels offer only a couple pieces of information. And so when you add ARRI to the retrieval with any of these space-based sensors, you're increasing about something around 2 degrees of freedom for temperature and around 1.5 to 2 degrees of freedom for water vapor. Now, where this information is coming from for ARRI and where the information is coming from for space-based sensors is very different. So I want to focus on the near surface layer. So we'll look at the surface to 700 hectopascals, where we see that ARRI has much greater information content than space-based sensors. So for both temperature and water vapor. Ultimately, when you add ARRI to the retrieval with AIRS or Chris or Yazzie, you end up doubling the information content compared to what's currently offered with AIRS, Chris, and Yazzie operating alone. So this is a significant improvement in the layer that we're most interested in. And then you end up with about a 40% increase in information content for water vapor as well in this near surface layer. So moving on to part B, the vertical resolution. This essentially refers to the thickness of the layer over which the signal is coming from. So you want your signal to come from a very thin layer if you want to know the temperature or water vapor of a particular layer. You want really thin, small vertical resolution is ultimately what we're going for. So I'll recall the averaging kernel again here. And again, remember that we're utilizing the diagonal elements of the averaging kernel to calculate the degrees of freedom. We end up using those exact same elements of that averaging kernel to basically spread that out across the vertical grid that we're using to calculate, that we're using for radiative transfer modeling, and that's our vertical resolution. So you can imagine that the coarse grid that the air's pressure levels have near the surface is going to limit what we measure area is capable of. And you can kind of see that here in the very bottom corner where the line is essentially straight because area is kind of bumping up against the vertical grid that we're using. So what we're looking at is vertical resolution of temperature is on the left, vertical resolution for water vapor is on the right. The shading in red is for airy, the blue is for crisp, and on the gray is for the combination of crisp plus airy. And so I'm shading between the 25th and 75th percentile for all the 4,500 approximately profiles that we're calculating averaging kernels for. And so what we find is that area is superior near the surface, specifically in the bottom 1,000 meters compared to crisp for both water vapor and temperature. And generally, crisp is better than airy above about 2,000, 3,000 meters above ground level. What I want to call your attention to, though, is this region here between about 500 meters and something around 5,000 meters above ground level, where the synergy of crisp plus airy is superior to either instrument operating alone. You can see that below that level, the synergy really leans on airy, and essentially has the same performance as airy, and above that level, it's really close to the same performance as crisp. But in this region in between here, you can see the value of a synergy or a combined retrieval compared to, say, let's use crisp above 1,000 meters and airy below 1,000 meters. The synergy would offer improvements in this 500 to 5,000 meter above ground level layer. So lastly, we'll look at uncertainties here. Once again, here's our averaging kernel. This quantity here that's being inverted in the center is actually the posterior error covariance matrix. And so ultimately our uncertainties are equal to the square root of the diagonal elements in S. And so these are kind of the same sort of figures that we saw previously. And so airy is better than crisp below 1,000 meters again, kind of the same exact thing that we're seeing for vertical resolution. Above 2,000 meters, crisp seems to be better than airy. This is largely what we'd expect. And then again, we see this region also in roughly the same area as we saw the vertical resolution improvements. The synergy is better than either instrument alone, between about 500 meters up to about 4,000 or 5,000 meters above ground level. I realized I forgot to note on this previous figure that the decadal survey calls for a sounding of, set a goal for 1,000 meter vertical resolution moving forward. And so you can see that with crisp alone, we're not really attaining that. However, with the synergy of crisp plus airy, we attain that, we reach that goal in the lowest 1,000 meters of the atmosphere, which I'd argue is the most important layer to know very well. And so I'll point out here too that the decadal survey calls for uncertainties of less than or equal to 1 Kelvin. And so again, you see that the synergy is reaching that goal actually throughout the entire troposphere here. Whereas on the water vapor mixing ratio side, excuse me, the synergy of crisp plus airy begins reaching that goal in the lowest 1,000 meters. So, a quick summary of this clear sky section. Adding the area to a retrieval with space-based sounder significantly improves information content, especially in the near surface layer. The synergy of Chris plus area begins approaching the goals of the decadal survey in the lowest 1,000 meters for both vertical resolution and uncertainty. And then we've identified this region between about 500 meters and something around 4,000 or 5,000 meters above ground level, where the synergy of Chris plus area is superior to either instrument alone. So next, we will move on to cloudy sky cases, cloudy sky information content. So what I do is kind of use 3 case study profiles, varying the cloud height. So a cloud base at 500 meters, 2,000 meters, and 3,000 meters above ground level. And then I'm going to look at how degrees of freedom varies with the cloud optical depth, and how degrees of freedom varies with cloud fraction. To make this talk shorter, and so that we're not here all day listening to me, I'm going to just focus on the 2,000 meter cloud-based case. So in order to, for cloudy sky, for radiative transfer modeling in the cloudy sky scenes, we need to account for scattering of the cloud layer in the infrared, and so we utilize the LBL dye-sort model that Dave Turner has made, and so this is called LBL DIS for short. Ultimately, what it does is it combines clear sky layer optical depths from LBL RTM with the dye-sort scattering model in order to calculate cloudy sky radiances. We are limited in how many levels we can put into this model, so we have to use a 500-meter grid instead of the AIRS pressure grid that we used earlier. And we're going to make some small perturbations to the profile and essentially rerun it in order to calculate Jacobians. So I'll start with how degrees of freedom varies with cloud optical depth. So what we're looking at on top is the above cloud, so the essentially defined as the top of the cloud top up to 200 hectopascals is what I'm defining as above cloud degrees of freedom, and then the below cloud degrees of freedom is the cloud base down to the surface. And plotted in purple is airy, plotted in orange is Chris, and plotted in green is the synergy of Chris plus airy. So we're looking at above cloud and below cloud degrees of freedom for temperature. Above cloud, airy begins decreasing in information content as the cloud fraction increases. Ultimately, this is because the optically thick cloud reduces the signal that airy is sensitive to above the cloud layer. Below the cloud, we see that airy increases information content as the cloud becomes optically thicker. So in order to understand what's going on there, I plotted the diagonal of the averaging kernel for varying cloud optical depths. So the black is the most optically thick cloud, and then this cyan color is clear sky. You recall that the diagonal of elements, basically we are taking the sum of what's plotted here to calculate the degrees of freedom. And so what we see is as the cloud becomes optically thick, this box here is where the cloud is located. Basically what we see is that that optically thick cloud presents a nice surface for airy to retrieve the temperature of. The reverse is seen for Chris. So above the cloud layer, Chris increases in information content, whereas below the cloud layer, Chris decreases in information content, ultimately because Chris can't see the surface as well anymore because of the thick cloud layer. And this is the same mechanism going on, that Chris becomes very sensitive to that cloud top as it becomes optically thick. Ultimately, what we find here is that the synergy of Chris plus airy will lean on Chris alone above the cloud when the cloud is optically thick, and then will lean on airy alone below the cloud layer when the cloud is optically thick. This is really what we'd expect because we're not expecting Chris to know much about the surface when there's a thick cloud there, and we're not expecting ARI to know much aloft when there's a thick cloud there. So it basically takes each sensor alone on either side of the cloud layer. Looking at water vapor now, so we get kind of the same thing above the cloud and below the cloud. We see that ARI, again, decreases in information content as the cloud becomes optically thicker. And this time, instead of increasing information content below the cloud layer, ARI has a slight decrease in information content as the cloud becomes thicker. You can see that progression in information content decrease here, kind of above 1,000 meters and below the cloud base. Ultimately, what's going on is these are clear sky water vapor Jacobians. This is water vapor Jacobians for cloud optical depth of 1, and then water vapor Jacobians for cloud optical depth of 40. Basically, what we see is that the cloud is saturating the spectrum, so it's radiance measurement that ARI is making, and so it becomes much less sensitive to small perturbations in water vapor. So returning to this figure, we'll look at Chris here. Chris doesn't really change information content above the cloud for water vapor, but it does decrease in water vapor information content below the cloud. Again, just like we'd expect. And then again, the synergy follows Chris alone above the cloud and follows ARI alone below the cloud. So if we move to a full troposphere view, so the surface up to 200 hectopascals, instead of partitioning this in above cloud and below cloud layers, we see that the synergy of Chris and ARI has significantly greater information content than Chris or ARI operating alone. And that difference becomes especially large for temperature as the cloud becomes optically thick. Ultimately, what's going on here is both Chris and ARI, being IR sensors, will lose information content when there's an optically thick cloud present. However, if we used a synergy, so introduce an ARI to the observing system and combine that with, say, Chris or Ozzy or AIRS, we could actually increase the possible temperature information and reduce our loss in water vapor information overall that Chris alone currently experiences. Just to show you that the same pattern exists in the other cases as well, this is the 3,000 meter cloud base and the 500 meter cloud base, kind of the exact same patterns we see. So a quick summary of this cloudy sky information content study with cloud optical depth. We really confirm our hypothesis that a synergy of ground-based and space-based sensors are going to lean on the space-based sensor above the cloud and lean on the ground-based sensor below the cloud when the cloud is optically thick. So we saw that clouds present a nice surface that makes it easy for Chris and ARI to retrieve the temperature of the cloud top and cloud base, respectively. However, I'll note that in order for these gains to actually be made in practice, it would require direct modeling of the cloud, which is kind of unpractical in an operational setting at the moment. And then lastly, we saw that water vapor sounding, especially from the ground-based perspective, becomes more difficult as the cloud becomes optically thicker. So now we'll move on to considering how degrees of freedom varies with cloud fraction. I'll note that we're only looking at the case where cloud optical depth is 40. So in order to calculate Jacobians in partly cloudy scenes, we can essentially take a weighted average of the clear sky Jacobians and the cloudy sky Jacobians, where n is the clear sky fraction. It's the clear sky or cloudy sky fraction. I'll note that ARI has such a small field of view that we can essentially assume that cloud cover for the area is binary, either 100% clear or 100% cloud. Chris, on the other hand, has quite a large field of view with a diameter of about 15 kilometers. In addition to that, the sensitivity of the field of view is not uniform, so therefore we really need to worry about the location of clouds as well. So if we wanted to know the location of clouds within the Chris field of view in practice, there is a Chris and Veers co-location data set that Dave Tobin has worked on in this building. And essentially that would allow us some knowledge of locations of clouds within the Chris field of view. So we'll follow that and essentially simulate the 375-meter grid that VIIRS has, and basically overlay that on the CRISP field of view in order to simulate the locations of clouds. So what we do here is this black line is our CRISP field of view. The black dots are our VIIRS grid, and then the shading is the CRISP sensitivity. So essentially, we're approximating that as a cone. So you're most sensitive in the center of the field of view and have very little sensitivity on the peripheries of the field of view. So ultimately what we find is instead of cloud fraction as the weighting for clear sky and cloudy sky Jacobians to calculate partly cloudy sky Jacobians, we need N is actually the total fraction of CRISP sensitivity that's either clear or cloudy. So what is the total sum of the sensitivity that's covered in cloudy sky, and what is the total sensitivity in clear sky? I'll note that we are assuming that the only difference across this grid is the presence of clouds. The same thermodynamic profile is used for calculating the clear sky Jacobians and the cloudy sky Jacobians. So it's the same thermodynamic profile being weighted in the partly cloudy sky Jacobians. So in order to simulate the locations of clouds, we'll do 3,000 simulations, essentially making random permutations of which pixels are clear and cloudy within the CRISP field of view. So what we have here is, this is essentially a histogram for the 25% aerial cloud fraction. And what we see is when 25% of the area of the field of view is covered with clouds, the sensitivity of the CRISP field of view that is covered in cloudy pixels can range anywhere from 22% to up to 28%. So there is a bit of variation there. And then this is for 50% and 75% cloud fraction. Now, randomly choosing which pixels are clear and cloudy might be a very rough approximation of scattered cumulus. We want to simulate a scene that kind of resembles an approaching cloud mass as well, so an approaching one-front type thing, where basically all the cloudy sky pixels are located on a single side of the field of view. So we get something like this, where the black dots are clear sky, and then the red dots are cloudy sky, and basically, as we increase aerial cloud fraction, that coverage increases like that. So what we'll look at here is the degrees of freedom for CRISP and the partly cloudy scene when we do this. So we have degrees of freedom for temperature and degrees of freedom for water vapor on the bottom. What we are looking at is the dark lines are actually, these are actually box plots of the lines. What we found is that the number 3,000 simulations we did, and the variations that we saw in CRISP sensitivity here from like 22% to 28% actually don't result in much change in information content in that. And then, sorry, I'm not explaining this very well. So the dark lines are measuring CRISP degrees of freedom for temperature above the cloud, red lines for below the cloud. Same thing for water vapor down here. And then the dots are for our warm front scenario. And so yeah, as I mentioned, these are supposed to be box plots, but they're so compressed on each other that there's hardly any variation. So these small x's that I plotted here are the mathematically feasible maximum and minimum sensitivity that can be covered in clear or cloudy pixels. So essentially, let's put all the clouds in the center of the field of view, and then let's put all the clouds on the edge of the field of view and see what happens. This isn't necessarily physical, but I wanted to get a greater sense of what is mathematically possible for our variations in information content based on the location of clouds within CRISP's field of view. So ultimately what we find is above the cloud, CRISP's information content increases, just like we saw for CRISP with the increasing cloud optical depth for temperature above the cloud. basically you have that cloud layer there, and it's able to become sensitive to the cloud top. And then the reverse is true for below the cloud. Chris's information content decreases as more clouds appear. On the water vapor side, we didn't see much variation in optical depth for Chris above the cloud, and this is repeated for water vapor. Below the cloud, Chris lost information content as the cloud became optically thicker, and the same thing happens here. I'll note that you're seeing that the degrees of freedom for Chris becomes most sensitive to changes in cloud fraction once that cloud fraction is greater than 50%. So once you get a cloud fraction greater than 50%, the influence of the clouds really starts to matter a lot. So now we're going to look at the synergy of Chris and Airy. So we're looking at above cloud degrees of freedom for temperature here, and below cloud degrees of freedom for temperature here. In this case, the dark and red lines represent, the dark line is when Airy is in clear sky, so there's no cloud above the Airy, and then the red line is when there's a cloud above the Airy. Ultimately, this is because Airy binary and is cloud covered. So what we see is that when there is the cloud there, Chris is able, essentially the synergy of Chris plus Airy becomes sensitive to Chris knowing that cloud top very well. So we increase information content, much like we saw the synergy do for increasing cloud optical depth again. Below the cloud, you're largely leaning on Airy. So this Airy had slightly greater information content when there was a cloud there, and so that's why the red line is greater than the dark line there. Moving to water vapor, so again, this is above cloud degrees of freedom for water vapor, and below cloud degrees of freedom for water vapor. We don't see any variations here, ultimately because Chris plus Airy didn't see much variation in water vapor above the cloud, and below the cloud, Airy had a slight decrease in information for when the cloud was present and when the cloud wasn't present. And so that's ultimately the difference in these two plots, two sets of lines down here. But ultimately, there's not much variation in water vapor, much like we saw for cloud optical depth. So our summary for this section is essentially increasing cloud fraction causes the degrees of freedom for both Chris and Chris plus Airy to behave somewhat similarly to increasing cloud optical depth. This kind of makes sense because you're adding more clouds. So if you calculated an optical depth of the field of view, you're going to see something similar. As you add more clouds, you're going to have greater optical depth in that field of view. We found that Chris is most sensitive when the cloud fraction is greater than 50%. We found that the location of the clouds are not necessarily very important in driving variability in information content, though I will note that Chris plus Airy reduces the variations that we saw. Those small variations we did see, Chris plus Airy reduces that dependence on cloud location. So lastly here, I'll try to go quick through this. We developed a kind of prototype of a combined retrieval, and we apply this to a case study from June 20th, where an area is located here at this black box in central Kansas. There was a Chris overpass on Suman MPP, and this is the field of regards plotted in dots here, colored by skin temperature. So you can see that the area falls nicely in between, within this granule, but between two fields of regard. And so we utilize an optimal estimation framework, which ultimately you're calculating. It's an iterative retrieval, and you're estimating the state vector x at the next iteration based on a first guess, which is usually a climatological mean, and then we remember this quantity as our posterior error covariance matrix. And really what you're iterating on is the difference between what we expect the measurements to be based on our current estimate of the state xn and that difference with what the actual measurements are. So you'll notice that there's this gamma factor here weighting the a priori. And so Dave Turner introduces this to basically allow the retrieval to overcome a poor first guess. You essentially weight the prior a lot early on in the retrieval and then decrease it as it decrease the value of gamma at later iterations. And basically slowly adding more value to the measurements in the retrieval. I found that the retrieval became very unstable at gamma equals 1, so I allowed convergence at gamma equals 5. When I met convergence criteria and gamma equaled 5, then I allowed the retrieval to converge and end, whereas Dave requires convergence at gamma equals 1. So, a quick look at temperature retrieval comparison here. We see we have the same colors as before, where orange is Chris alone, purple is Airy alone, and the green is the synergy of Chris plus Airy. The black dotted line is a radiosonde measurement, so we're looking at temperature here. Ultimately, what we see is that Airy alone has the best representation of the near surface inversion, and then the synergy of Chris plus Airy is improved kind of from what Chris suggests, though it's not as good as what Airy alone offers. So this is kind of going against what we would have expected based on our information content studies earlier on. On the water vapor side, kind of the same thing is happening. We see that Airy has a really good estimate of the water vapor profile near the surface, and then the synergy of Chris plus Airy is better than Chris alone, but still worse than Airy alone. You can see that Chris and the synergy of the two sensors is kind of sensitive to these two upper level voice layers, though that signal kind of gets spread out by the vertical resolution up there. So that's a little discouraging that our synergy isn't solving all of our problems with comparisons to radiosondes. We can look at vertical resolution though of the retrieval, and we encouragingly see that the retrieval is recreating the improvements in vertical resolution that the information content study suggested. So the synergy of Chris plus Airy has superior vertical resolution to either sensor alone throughout most of the profile here. And then the same general thing is seen for water vapor. In terms of uncertainties, that kind of goes out the window. So what we find is that the synergy of Chris and Airy actually has greater uncertainty than either sensor operating alone. So this is completely opposite from what we would have expected from our information content study. And the same general thing happens with the water vapor retrieval. So one thing, this kind of phenomenon was identified by Aries in 2011 when basically found that when you combine multiple instruments into a retrieval, one instrument could have uncertainties that are ultimately too small and dominate the retrieval. So I basically asked the question, what happens if we artificially increase the noise? So I multiply the noise by 5, and we see that now our uncertainties essentially recreate what we would have expected from the information content study. So the synergy of Chris and Airy is superior to either instrument alone throughout the profile. And we kind of see the similar regions where the synergy converges to Chris and converges to Airy alone. Unfortunately, that doesn't solve our issues for the comparison to radiosonde observations. It actually makes the retrieval for water vapor of the synergy worse than either sensor alone. So this ultimately isn't the final answer, though getting our uncertainty profiles to recreate what we would expect is certainly a step in the right direction there. So, summary of our retrieval here. Chris and Airy doesn't have the best comparison to the radiosonde, which is unfortunate that it's not solving our problems real easily. I suppose it's possible that this averages out over time, but I think some future work is needed to get it to that stage, which I'll touch on in the next slide. I will note, and it's very encouraging that the Retrieval replicated the improvements in vertical resolution that we saw from the information content study. And it's really important that this exceeds the goals of the decadal survey in the lowest 1,000 meters, which I'd argue, again, is the layer we're most concerned about for improving sound. So as I mentioned, Chris plus Airy had greater uncertainties than either sensor alone, likely because the uncertainties are ultimately too small for each instrument. So two instruments are telling the Synergy two very different things, and the Retrieval has no idea what to do with the two different signals. So therefore, we need to find other sources of error to include within our error covariance matrix. So that's kind of one direction of future work. How do we increase the uncertainties in a meaningful way? And then second is kind of extending this beyond one case study, and kind of trying to get a larger data set of area matchups with our polar orbiting sounders. And then ultimately the big question hovering over all this work is that I haven't addressed, and other work in the literature has yet to address as well, is how important are the heterogeneities within the space-based sensor's field of view? And then there's also the offset distance between what field of view is the closest matchup with the ground-based sensor. So how do those influence how the synergy is going to work in practice? So I'll leave my conclusions for after. I'll leave this slide up. First, I want to acknowledge, though, some very important people in getting me to this point. So I want to thank Tim and Steve for advising me, especially Tim for doing the weekly grind with me and asking me hard questions every week for the last however many years it's been. I want to thank Steve and Wayne for taking a chance on me in 2014 when I was applying here as a graduate student. I want to thank Bob Knudsen here at SSEC and Dave Turner at NOAA for their mentorship and comments throughout this project, really helping guide me and also asking important questions and giving me important insights. I want to thank my committee members, Ankur, Michael, and Tristan, for all the time that you've spent mentoring me and asking questions as well. I want to thank my first-year classmates who have pretty much all moved on by now, but Alex, Kai Wei, Kate, Keiko, Luke, and Marion, you guys made those first-year classes much more enjoyable working together than going at it alone, so I thank you for that. I want to thank my family, especially my parents, for giving me the freedom to turn my interest in weather into way too many years of schooling. And ultimately, at the end, I want to thank my wife, Michelle, for all of her support, especially all the sacrifices you've made in the last 6 months here. And I hope that this achievement is as much yours as it is mine. So thank you to those people, and I'll leave my conclusions up here, and yeah, I'll take questions.
So I'm going to suggest, David, that you take questions from in here and every now and then check with Pete and see if there are any things that are online, rather than three of us trying to dance.
Brad?
You mentioned at the beginning that you're kind of underestimating the observational error because you're not really accounting for the model error. But you're looking at cases that are co-located, right? That was
Say that again?
You're looking at cases where you've got radio sons that are co-located with Chris or something.
The radio son measurements from ARM are definitely co-located with ARI, but I haven't actually confirmed that they're co-located with a Chris or Yazzie or ARIS.
Could you get a better estimate of your forward model errors by comparing, your actual radiances?
I suppose that's a good path forward, like an odds minus calcs type thing.
Yeah.
Dave Turner has also sent me a paper by Domenico Cimini that kind of had a more sophisticated way of accounting for model errors, essentially like taking standard deviations of line parameters and kind of building that out to what's that uncertainty in radiance space. And so, yeah, there's several paths forward there, but I think the optimized calcs would be a much simpler.
Top down versus bottom up.
Yeah, it would be a much simpler, more straightforward method for giving something at least, yeah, to inflate.
For all these calculations, you're using all the spectral bands that are available.
Correct, yeah.
It would be interesting and valuable for the NWP to do the same degrees of freedom with the limited bands that they're actually assimilating.
Yes, that is a goal that I have, is to rerun this, especially like with the discussion on the short wave versus the long wave. What's more important, I kind of want to develop an opinion on that and throw my hat into the ring on that too. So yeah, this framework is very easy to adjust for channel selection. So yeah, that's definitely a piece of future work.
Right, this may follow on from
Yeah.
Brad's question, but that gamma factor that I guess Dave Turner suggested in the solution to the algorithm, you start off with a high value of it and then slowly decrease it.
Yes.
Do you think that may be playing a role in why you seem to be seeing some benefit from inflating the observational error? Because if you're going to heavily weight the background error initially, I'm wondering, again, given there's some issue about the uniqueness of the solution, I'm wondering if you're possibly arriving at a solution that's not
Yes.
closest to reality.
So when I did run the retrieval with 5 times the noise and with the gamma factor, it A, converged much quicker, and B, I only showed where I kept gamma at 5 because I only let it go down to 5 because that's what made it work for the base state. But yeah, it did end up converging at like gamma equal 1. So I do think that is a big reason why my retrieval is unstable for low gamma, because it needs that inflation in the errors.
Yes.
So I'm just curious if, so do you anticipate any additional considerations for, like, working on your retrieval, if you were to apply or do a case study in part of the globe where the planetary boundary layer may be behaving differently, such as like in the subtropics, where there's an increased amount of subsidence and it may be like inversion lower in the atmosphere?
Sure. So is your question more directed at the actual retrieval applied to real observations, or like more like in general?
I suppose, yeah, it is kind of a tricky question
I
because you
guess-
have to make sure that you have the observations first.
Yes. So I guess what I'll say is, based on my results from the information content study,
Yeah.
the synthetic study, and kind of looking at a whole bunch of different scenes, there is large variation, as you saw in those box plots. If I go find them again. So like there is large variation in like I did look at, say, like how this information content varies with precipitable water, and so there are some changes with precipitable water vapor. So I do think it'll be a little different, but ultimately I'm very confident that the same, like if we get the retrieval working, like we should be able to replicate what the information content studies are finding, which is that the synergy is much better, and that's regardless the environment that it's performing in. Does that answer your question?
Yeah.
Interesting.
Just ask a question, because something I was wondering when I was looking through the dissertation. So if you did create a retrieval that actually worked with AIRS, CRIS, IAZI, probably not ABI for now, but I mean, in lieu of the fact that we don't yet have geostationary hyperspectral sounder, how many times a day could you actually do soundings over an AIRI site? So you were saying basically you want to supplement the twice daily soundings. Do you have an idea for how many times the full, if you use the full swath of these instruments, you'd actually be able to, like what kind of time resolution would you get?
Yeah, so ultimately you're going to end up with, so what, there's AIRS and CRIS are in the A train, so those, and there's 2 CRISs and one errors. So those three kind of come in a batch, so they aren't right on top of each other though. So you kind of would have three several tens of minutes apart, and then 6 hours later you'll have the three Yazis in the meta series, kind of 1, 2, 3, same sort of thing. And so that would, let's see, so you'd kind of have 4 overpasses in a given day. So, and at least in North America, that's conveniently located between the 0 and 12Z radio zones. So particularly important for the convective initiation cycle during the day. So it can't hurt having more value there, certainly. And I know that there's been work getting new caps into like AWIPs, and forecasters starting to use CRIS alone, like CRIS and Yazi alone type retrievals in assessing convective like stability between those radio song times. So I think that sort of potential is there. Ultimately, of course, the geosounder is ideal, but in the meantime, kind of take what we can get. And it's not bad in terms of the timing that we have those overpasses. There's a lot of information that can be gleaned from that.
We do have some questions online. First of all, there was some clapping, although I have to say it was great to hear actual clapping. It's been a while. Tim Schmidt asks, how might more rapid soundings, say 30 minutes from geosensors, help low-level retrievals of moisture? Sounds like you're just touching on that.
So, I mean, I think ultimately the synergy, like, is he asking about a synergy or just kind of?
The question is, how might more rapid soundings, say 30 minutes from geosensors, help low-level retrievals of moisture? I'll see if he follows up. They're a little behind though.
So I think ultimately you're going to have the same information content, whether you're roughly the same information content, whether you're sending right now at 11 a.m. or in 15 minutes at 11:15. Where that sort of rapid sounding is important is you start, so kind of like Maria Tokarov's study, you're able to identify these trends, like CAPE is increasing rapidly here, whereas if you had, like we currently have with CRIS and Yazi and kind of separate 6-hour increments, you'd have like, you might have a measurement here and a measurement here, and it's like, well, we already missed the big increase of CAPE, and so we kind of missed the severe potential because it's probably already ongoing type of thing.
He said yes, synergy. Next question from Paul Menzel. Nice work. To improve CRIS performance, would you double the spectral resolution or half the FOV size?
Or both?
Or both.
So,
As long as we're asking for 30s here.
So I don't know how much either matters because, so we have a comparison of CRIS with the Yazi here. And Yazi has superior vertical resolution, or superior spectral resolution throughout the entire IR spectrum that it covers. And it has like 8 times the channels that CRIS has because it covers the full spectrum instead of the 3 distinct bands like CRIS has. And so I guess CRIS has lower noise, so I guess you might increase information content a bit from decreasing the noise, but I'm kind of finding that the noise is already too low to start with, so it might make our combined retrieval more difficult.
Okay, one last one from online from Curtis Walker. What are the future steps to expand and improve this work?
So really the 2 big ones is kind of getting the retrieval to be stable and converge, so ultimately finding new sources of errors to include in the error covariance matrix, and then once we get that working, kind of get a large data set of matchups with the polar orbiting overpasses and start validating this, see if how close the retrieval uncertainties are to actual comparisons of radio songs, that type of thing. So it's all on the real observation side. I think we've We know a lot on the synthetic information content side, but I think a lot more work is needed on the real observation side. Steve?
So you had a general question. As a co-chair of the 2017 decadal study, of which Paul was on as well, there was a lot of discussion about this 1 degree C temperature, 1 kilometer vertical resolution. We got, 5, 6 years left in that decade. Did we get it wrong? Will it not be achievable?
I don't know how, I don't have a full grasp on other technologies at this point, but I definitely don't think you're going to. So I've kind of rigged the system in this information content study, right, to kind of make it as good as possible, especially from the space-based sounding perspective. I'm using their grid, I'm only using really small instrument noise, not accounting for other errors, and we're nowhere near that goal. And if I included skin temperature in the retrieval, Chris never gets anywhere near 1 kilometer vertical resolution for sounding. So, and given how close EASI is in the superior spectral resolution there, I don't think we're ever going to get there with passive sensors at least. We need some sort of active sensor, like a water vapor dial, to at least get the water vapor really well, and that might tighten up the temperature retrieval type thing. But I don't think passive sensors would achieve the decadal survey goals. Though I am pretty confident that a synergy of introducing the area to the observing system would at least achieve the goal of the surface. Does that answer your question?
Unfortunately, yes.
Any other questions? Cool. Thank you very much, everyone, for coming.